Before the second day of class, you should quickly skim through Chapter 1 of Mazur's book, which doesn't contain much substance. There are a couple of things like unit conversions and estimation, but it should be a quick skim. Normally, I would have you read the textbook chapter before watching the video, but I think in this case, the video should help you to skim more quickly and efficiently through the chapter. So you could do it either way, but I think it's probably more straightforward this time if you watch this video, which covers Mazur Chapter 2, and then skim through Mazur Chapter 2. And I hope that after you've gone through this video, you can get through that chapter very quickly. So the main topic of Chapter 2 is vectors. Well, it's motion in one dimension, but a big part of it is vectors and a couple of examples of vectors. So a vector has both a magnitude and a spatial direction. So instead of just saying 5 meters or 3 miles or 2 blocks, we say 5 meters up or 3 miles north or 2 blocks east or so on. So it's important to include a direction. So we will soon meet a vector called the velocity, and it will, for example, be written like v with an arrow over it. The arrow reminds us that it has a direction, and it will have components v sub x, v sub y, and v sub z. So that's the velocity, the x component of velocity, the y component of velocity, the z component of velocity. This is the typical case for vectors in three-dimensional space. We have 3 coordinates because there are 3 dimensions to our spatial world. You could call them east-west and north-south and up-down, for example. But there is a special case vector, which we call r, which has components x, y, and z. So we don't normally write r sub x for the x component of the r vector. If we did, it would be x. And we don't normally write r sub y for the y component of the r vector. If we did, it would be y. And we don't normally write r sub z for the z component of the r vector. If we did, it would be z. So instead, we just say x, we say y, we say z. It's not clear what letter to associate with this combination x, y, z, so we just say r. By the way, I wrote this as an ordered triplet. So from a secondary school math class, you may have studied vectors in the plane, and often we used y for the vertical axis and x for the horizontal axis. And we might choose some point in the plane, maybe some point over here, and we would call that, maybe it's like a point P, but anyway, let's just give it coordinates x comma y, written as an ordered pair. So we call this the origin. The origin would be like 0, 0. It would be like x equals 0, y equals 0. So we usually use like a capital O to represent the origin. And then this distance up from the horizontal axis we call y, and this distance over from the vertical axis we call x. And then we often, in secondary school math class, write this as an ordered pair, x comma y. And then if you took high school physics, you probably learned to generalize this to x comma y comma z. You might have seen it in like your calculus class also. So for 3-dimensional vectors. So I think you might be accustomed to writing vectors in the plane as ordered pairs, x comma y. And you might have also seen writing vectors in 3-dimensional space as ordered triplets, x comma y comma z. So I will often use that notation because I believe it is familiar to you. I remember learning it in secondary school, and probably you did too. But Mazur never uses this ordered pair or ordered triplet notation, so just bear that in mind. He uses this other notation using unit vectors that none of the students in this course ever like, but I'm just going to, we'll see it so we know what it is when we see it. So if you think of your secondary school days studying the XY plane, then this vector r points from the origin to some point x comma y. So that is sort of a vector we typically think of as representing an arrow pointing from the origin. The tail is at the origin. The head of the arrow is at the point xy that we represent. Although we also think of this ordered pair xy as simply representing this position, sort of this dot on the plane. But most of the time we think of a vector as an arrow. And so in this case, it's an arrow from the origin to this point xy. And then, every coordinate system has an origin. Sometimes it's somewhat arbitrary what you call the origin, but you do need to keep track of what you call the origin. If we take a vector in 3 dimensions, like say this position vector x, y, z, the magnitude of r is written like this. It's like the norm or like the absolute value of r, and sometimes it's also just written plain old r without the arrows to indicate the magnitude of r. And in 3-dimensional space, this will be x squared plus y squared plus z squared. And that velocity vector that I drew earlier, so the magnitude of that velocity vector we just call v, which turns out to be the speed. And its magnitude will be the x component of velocity squared plus the y component of velocity squared plus the z component of velocity squared. So that's the Pythagorean theorem at work. But in this course, using Eric Mazur's textbook, for the first 9 chapters of the textbook, all vectors will be in 1 dimension. So that means there will only be an x component. There will not be any y component. There will not be any z component. So we only have to worry about one axis. We won't have a y-axis. We'll only have an x-axis. If you're accustomed to the y-axis pointing up, when we deal with problems in the first 9 chapters that have up and down motion, we will, which you might find a little counterintuitive at first, we will use the axis called x. So we will make the x-axis point upward sometimes when dealing with vertical motion in the first 9 chapters. It takes a little getting used to. Anyway, the whole idea is we don't want to use too much math for the first 9 chapters. We want to focus on the physics. And then once we've kind of built up our intuition with, thinking mainly about the physics and not so much about the math, then we get to chapter 10, we'll go back to motion of plane. We'll deal with 2 dimensions. And later we can generalize to 3 dimensions. So keep that in mind. You know that the magnitude of the position vector involves the Pythagorean theorem, and then you'll see that in general, if you have 3 components of velocity vector, you need to use the Pythagorean theorem to get the speed, which is the magnitude of that vector. But we won't do that until about a month from now when we get to chapter 10. Let's work through a couple of examples here using as our coordinate system the city blocks on Walnut Street between DRL, where our class meets, and Addams Hall, where many of you spend a lot of your time if you're in the architecture program. So what is the distance in blocks between DRL and Addams? So 1, 2, 3, I would say that's 3 blocks. The distance between DRL and Addams is 3 blocks. How did we do that? We took our ending position minus our starting position. So that's subtract. We subtract the starting position from the ending position, and we take the absolute value. That's the distance. And we'll do this writing out more steps in a minute. If you walk in a straight line, it starts at DRL and ends at Addams. What is your distance traveled? Now, we're going to use a term called distance traveled in this course, which has a slightly different definition from distance. The distance will be how far apart are your starting point and your ending point. The distance traveled will be, it's sort of like how much did your odometer in your car increase as you made the trip. if you just go from point A directly to point B, there's no difference. But if you go forward and then backward and then forward and then backward and then forward again, then your distance traveled is different from the distance between your starting point and your ending point. So that's an important distinction. Every time we change direction, we have to break up the trip into a new segment, and we take the distances of all of those individual segments and add them together to get the distance traveled. So we'll write that down in a minute also. So bear that in mind. The distance traveled has to be broken up into steps if you change direction. It's different from just the distance between your starting and ending points. So what is your distance traveled if you walk in a straight line that starts at DRL and ends in Addams? I would say it's 1, 2, 3 blocks, because I didn't change direction and I started out, let's say, at x equals 33. I ended at x equals 36. That's a difference of 3 blocks. An absolute value is 3 blocks, so that's it, 3 blocks. What is your displacement expressed using blocks and a compass direction? Okay, so if we started at DRL and ended at Addams, then we want both the magnitude and the direction of our displacement. And we'll write down displacement more formally in a minute. We went 1, 2, 3 blocks west. So I would say if we go from DRL to Addams in a straight line, our displacement is 3 blocks west. So the magnitude is 3 blocks, the direction is west. To make it a vector, we say both 3 blocks west. If you start at Addams and end at DRL, what is your displacement? Okay, I start at Addams, I end at DRL, so that's 1, 2, 3. So if I start at Addams and end at DRL, my displacement is 3 blocks east. Or I could say it's negative 3 blocks west. If I happen to have made my x-axis point in the west direction, maybe I want to always say west, and so then if I travel east, I'll say I travel a negative number of blocks west. So I could say negative 3 blocks west, or I could say 3 blocks east. What is my distance traveled in that case? Well, it's 3 blocks. So in the first case, my displacement was 3 blocks west. In the second case, my displacement was 3 blocks east. In both cases, my distance traveled was 3 blocks. If you start at Addams, walk to Meyerson, walk back to Addams, then walk to DRL, ending there, what is your displacement? Whoa. I think we're going to have to draw a little bit more detail to be able to remember that. So let's see. So we start at Addams, and we walk to Meyerson. So that's our first segment. And then we walk back to Addams. That's our second segment. And then we walk to DRL, and that's where we end. Okay. So if we want to work that out, then we need to add the lengths of these 3 segments, because you see at this point we change direction, and at this point we change direction. So here's the starting point. The starting point is at 36th Street, and the ending point is at 33rd Street. So you might think that the distance is just the 3 blocks between our starting point and our ending point. But the distance traveled, in other words, how much would our car's odometer have increased? Or, how much credit would I get for taking steps if I have to walk some number of steps per day for keep my smartphone happy? Then this is 2 blocks plus 2 more blocks plus 3 more blocks. That's 2 plus 2, 2 plus 2 plus 3. That's 4 plus 3 is 7. So, that was my distance traveled, sorry. So 2 plus 2 plus 3 is 7. So 7 blocks was my distance traveled for this back and forth trip. But my displacement only cares about my starting and ending points. So my displacement, I started at 36th and I ended at 33rd. So my displacement was 3 blocks east, or you could say negative 3 blocks west. So this trip where I go from Addams to Meyerson, back to Addams, and over to DRL, that displacement is the same as the displacement when I just walked from Addams straight to DRL. So the displacement in this case, Addams to DRL versus Addams to Meyerson to Addams to DRL, in either of those two cases, the displacement is 3 blocks east. It's my final position minus my initial position, both written in vector form. So that's 3 blocks east. But in this case, my distance traveled was 7 blocks, whereas in the original case, my distance traveled was just 3 blocks. You see, because I went here and then back and then back. So that's 7 blocks total that I covered, my odometer increasing. So there's some definitions we're gonna write down. For our next example, let's use my sort of crude map of the United States, and let's say we're traveling back and forth between San Francisco and Washington, D.C. So what is roughly the distance between San Francisco and Washington, D.C.? Well, I think it's about 3,000 miles, which turns out to be about 5,000 kilometers. Since we like metric units in this course, let's say it's about 5,000 kilometers. Okay. If you start in San Francisco and you end in DC, what is your displacement? I would say in this case, I have traveled 5,000 kilometers to the east. So I'm going to say 5,000 kilometers east. So that's a magnitude and a direction. So that's a vector. Which one is a vector? Oh, this is a vector. This is not a vector. So the displacement has a magnitude and a direction. The distance has only a magnitude. So this is a vector. Displacement is a vector. Distance is not a vector. Okay, so which one is a vector? Displacement. How does the distance between San Francisco and DC relate to the displacement from San Francisco to DC? Well, the distance is basically the magnitude of the displacement. So this is 5,000 kilometers east. That has a magnitude and a direction. If we just take the magnitude part, and we usually use the absolute value sign to represent the magnitude of a vector. We also sometimes call it the vector norm. Let's call it the magnitude or the vector norm. It looks like an absolute value sign. Sometimes it's written with 2 vertical lines instead of 2 double vertical lines. But so the distance between San Francisco and DC is just the magnitude of my displacement when I go from San Francisco to DC. So I guess I could say distance is the magnitude of the displacement, which is a vector. Okay. How does the distance between San Francisco and DC relate to the displacement from DC to San Francisco? Well, actually, this is true still. So the distance between San Francisco and DC is the same as the distance between DC and San Francisco. It's just the magnitude. The magnitude is 5,000 kilometers. But the displacement from San Francisco to DC is 5,000 kilometers east. The displacement from DC to San Francisco is 5,000 kilometers west, which you could also call negative 5,000 kilometers east if you wanted to, if you happen to have chosen your x-axis to point east and maybe you want to do things in terms of the x-axis. So again, I would say that the distance is the absolute value of the displacement, which is a vector. And actually, in just a moment, we're going to use better letters for this. We're going to say that this distance is the magnitude of delta r. So we'll use delta r, the vector, to mean the displacement, and we'll use a lowercase d for the distance in a moment. For a journey on which I go in a straight line, never changing direction, how are distance and distance traveled related? Well, we encountered that in the previous page when we went from Addams to Meyerson back to Addams to DRL. There we were changing direction. So if you never change direction, then distance and distance traveled are the same. So in this case, they're the same. Okay. For a journey on which I do change direction several times, how can I figure out the distance traveled? Well, I have to split the trip up into segments where for each segment I don't change direction. So I have to every time I change direction, I have to start a new segment. I split the trip up into segments and I add up the lengths of all of those segments. So I'm going to say the distance traveled is, let's say, D1 plus D2 plus D3, whatever. However many segments there are. And how many segments are there? There's one segment plus however many times I change direction. If I never change direction, it's just one segment. If I change direction once, I have two segments. If I change direction twice, I have three segments. So then we work out the distances of those individual segments and add them together to get the distance traveled. Okay, here we are finally writing down some definitions. So a vector has both a magnitude and a spatial direction. We said that before, like 5 miles east, 10 meters up, and so on. The position vector is a vector x, y, z pointing from the origin, which is 0, 0, 0, or you could just say capital O, to the object's location in space. Okay, we said that before. If an object moves from some initial position, R initial, so we will usually say R I, subscript I for initial. We're going to go from R initial to R final. So there's a little arrow on top of R to indicate that it's a vector. And this is our initial position. This is our final position. So we have a displacement, which we call delta R, which is R final minus R initial. And if we were drawing things, I don't know, on a plane, let's say, or on a map, and if this point on the map represents R initial, and if this point on the map represents R final, then this is delta R. So the delta R vector points from R initial to R final. Now technically, this vector R initial points from the origin to R initial, and this vector R final points from the origin to that point R final. But you might remember that when you subtract, well, if you want to be formal and say, what is R final minus R initial? We take R final and then we add to it the negative of R initial. The negative of R initial would point back this way, and then you could translate that over to here, and then you go tip to tail and you have a vector that has this, that looks like this. It goes from the origin to this point over here, and that is the same vector as this vector that goes from R initial to R final. It's a little bit tricky, but it's the same. See, it has the same magnitude, it has the same direction. It's just that we put its tip, we put its tail in different places. That may have been unnecessarily confusing. In any case, this vector delta R points from R initial to R final. So displacement is a vector, points from where you started to where you finish. The distance between R initial and R final is d, which is just the magnitude of the displacement vector, which can also be written as the magnitude of this difference, R final minus R initial. Then of course we have to know how to subtract vectors. And in one dimension, so in one-dimensional space, which we're going to be in for the first 9 chapters, this distance d is just the absolute value of x final minus x initial. Okay, so if I start at 33rd Street and I go to 36th Street, then the distance is just the absolute value of 36 minus 3, and then we're measuring in blocks, so the distance is just 3 blocks. So we're going to see when we get to motion in a plane in chapter 10 that in 2 dimensions you can say that the distance is the square root of delta x, the quantity squared, plus delta y, the quantity squared. And then if you even wanted to generalize to 3 dimensions, you could say delta x, the quantity squared, plus delta y, the quantity squared, plus delta z, the quantity squared. But for the first 9 chapters, we're working in 1 dimension, so this is good enough for us. So we have a scalar quantity called distance. So scalar means it has a magnitude, it does not have a direction. So the scalar distance, the distance between r initial and r final, is called d, which is the magnitude of delta r, which is the magnitude of r final minus r initial. And in 1 dimension, this distance is just the absolute value of x final minus x initial. So if the object does not change direction between r initial and r final, then the distance traveled is the same as d. If the object does change direction, for example, suppose we go from the initial point to A, and then to B, and then to C, and then to the final points. We're going from initial to A to B to C to final, and suppose that we change direction at A, and we change direction at B, and we change direction at C. In that case, the distance traveled is the distance from the initial point to A plus the distance from A to B plus the distance from B to C plus the distance from C to F. So that's like this vector difference, right? Displacement, the magnitude of the displacement from initial to A plus the magnitude of the displacement from A to B plus the magnitude of the displacement from B to C plus the magnitude of the displacement from C to the final point. Now, we're going to be working in 1 dimension for a while. So in 1 dimension, the distance traveled for this case would be, so in 1 dimension, this would be x A minus x initial absolute value plus x B minus x A absolute value plus x C minus x B absolute value plus x final minus x C absolute value. This is in 1 dimension. Okay, so the distance traveled in 1 dimension, assuming that we change direction at points A, B, and C, is the delta is, delta x, the magnitude. So it's xa minus xi, that magnitude, xb minus xa, that magnitude, xc minus xb, that magnitude, x final minus xc, that magnitude, and you add those 4 magnitudes together. So that's how you do the distance traveled in 1 dimension. You just have to work out where it is that you changed direction. Now, if someone asks you how to get from DRL to 30th Street Station, is it good enough to say without any pointing, just go 5 blocks? I don't think so, because you don't know which direction to go. What if somebody says go 2 blocks and then go another 3 blocks? Again, I don't think that's good enough because you don't know which direction. What about go 2 blocks north, then go 3 blocks east? I think that works because 2 blocks north from DRL would get you to 33rd and Market, and then 3 blocks east would get you to 30th and Market, which is where 30th Street Station is. So 2 blocks north, then 3 blocks east. So it seems like we need both magnitude and direction to get the correct displacement. So once again, first 9 chapters of the book, directions will be any given problem. It's going to be entirely north-south, or entirely east-west, or entirely up-down, or entirely forward-backward. There's going to be just one direction in the problem, just one axis to work with. You might go forward or backward, but there will be always along one axis. And finally, we'll get to chapter 10, we'll start generalizing to a plane. And it's a little confusing that we're using this language of vectors, because you say, well, why do you need vectors if everything is in 1 dimension? But you still have to distinguish between forward and backward. You still have to, even if it's just the east-west direction, there's a difference between 5 blocks east versus 5 blocks west. And I said this before, it's also, if you took physics before, you're used to up and down things being called y. Everything is going to be called x for the first 9 chapters. You'll just have to get used to that. We have here a graph. Time goes from 0 seconds. There's 0, 1, 2, 3. So time goes from 0 seconds to 3 seconds. And position goes from x equals 0 meters to 7 meters. Okay. So the question is, what is the distance traveled from time 0 to time 3 seconds? Well, do we ever change direction here? I mean, in other words, do we ever change from moving forward to moving backward? Which is what changing direction is in one dimension. I say no. I think we're always going forward. It appears that we're going forward at different speeds in these 3 segments, but we're always going forward. So we don't have to, we can just take the beginning to the end. So we have the distance traveled, in this case, is the same thing as the distance, which in one dimension is just x final minus x initial. And which is, that's the absolute value of 7 meters minus 1 meter, which is 6 meters. So our distance traveled in this case is 6 meters. What is the x component of displacement from 0 seconds to 3 seconds? Well, the x component of displacement is x component of delta r, which is displacement, is delta x, which equals x final minus x initial, which is 7 meters minus 1 meter, which is 6 meters. So I guess the x component of displacement is 6 meters. Now we've changed the problem a little bit. We basically reversed course. Now what is the x component of displacement? Well, now the x component of displacement, delta r is the displacement vector, is delta x, which is x final minus x initial, which is 1 meter minus 7 meters, which is minus 6 meters. So in the previous graph, the x component of displacement was plus 6 meters. In this graph, the x component of displacement is minus 6 meters. In both cases, though, the distance traveled is 6 meters. Oh, now in this case, whoa, okay. So now, what is the distance traveled? Well, we can look and see which of these things are still true before we erase them. So you see, x final is still 1 meter, and x initial is still 7 meters. So I guess the x component of displacement is still minus 6 meters, for example. But, okay, what is the distance traveled? So we have to ask ourselves, in this case, do we ever change direction? So do we ever change from going forward to going backward, or from going backward to going forward? And I think we do, because I think we're going backward from 7 meters. Well, we're going backward here in this interval. And then we're going forward in this interval, and then we're going backward in this interval. So I think somehow we have to split this up into 3 segments because we're going backward here, forward here, and backward here. So we change direction twice. So the distance traveled is going to have 3 pieces which we have to add together, right? Because we change direction twice, we have 3 segments whose lengths to add together to get the distance traveled. So let's do that. So it seems like, and we can call this point A, we can call this point B, we don't have to be quite so formal. But remember, we said before that the distance traveled, in this case, would be XA minus X initial magnitude plus XB minus XA absolute value plus X final minus XB absolute value. So what is that? So this seems like this is 3 meters. 3 meters minus, this is, whoops, that's 3, that's 4. So that's 3 meters minus 7 meters absolute value plus 4 meters minus 3 meters absolute value plus 1 meter minus 4 meters absolute value. So that is 4 meters plus 1 meter plus 3 meters equals 8 meters. Now let's just stand back and see if that makes sense. So 1, 2, 3, 4. So this is a distance of 4. There's 1. That's 5 total. And then 6, 7, 8. Yeah. See? 1, 2, 3, 4, 5, 6, 7, 8. You want to say how much did your odometer change? That's 8 meters that your odometer changed. Okay. So the distance traveled in this case was 8 meters. So because we changed direction twice, we had to add 3 different segment lengths together. Let's go back to this simplified map of the blocks of Walnut Street between DRL and Addams Hall. And to keep things simple, let's pretend that a city block is always precisely 100 meters long. So let's say this is 100 meters, 100 meters, 100 meters. So if I bike directly from DRL to Addams in 100 seconds, what is my average speed? Well, average speed, which we usually say is VAV, is the distance traveled divided by the elapsed time. So the distance traveled is 1, 2, 300 meters, and the elapsed time is 100 seconds. So this is 300 meters divided by 100 seconds is 3 meters per second. Average speed is distance traveled divided by the elapsed time. What is my average velocity? Well, average velocity is displacement divided by elapsed time. What is my displacement? So this is the same thing as saying displacement, which is a vector, divided by elapsed time. My displacement when I go from DRL to Addams is 300 meters west. and the time is 100 seconds. So in that case, my average velocity is 3 meters per second west. And that is a vector. It has a magnitude and a direction. So I bike directly from DRL to Addams in 100 seconds. That's 300 meters. I went west. 3 meters per second west. Right. Now, if I walk directly from DRL to Addams in 200 seconds, instead of biking, I'm walking and it took me 200 seconds. Oh, and then I bike directly back to Addams to DRL in 100 seconds. Whoa, okay. So I'm going to walk. Actually, you know, this is almost worth making a graph of. So we could say we have 36, 35, 34, 33, and then here's time. So it seems like 200 seconds and 100, yeah. So here's 100 seconds, 200 seconds, 300 seconds. Let's say 100, 200, 300 seconds. So what am I doing? I'm going from DRL to Addams in 200 seconds, like this. That's my first segment. And then I'm biking back from Addams to DRL in 100 seconds, like that. So it's a little hard to see, but the magnitude of this slope should be half because of the magnitude of this slope, because I've traveled 300 meters in 200 seconds here, and I've traveled 300 meters the other direction, only 100 seconds here. So that's what I did for like x versus t. Maybe that was more complicated than we needed just to answer this question. So this is walking, and this is biking. What is my average velocity for the journey? Oh, this was really a lot of work to answer this question, because average velocity is displacement divided by elapsed time. Well, the elapsed time was 300 seconds. What is the displacement? If I start at DRL and I end at DRL, what's my displacement? My displacement is 0. So in this case, my average velocity is 0. You could say with an arrow, I guess, if you want to, but it's 0 meters per second, I guess. Yeah, so you see my displacement is 0 and the time is finite. So my average velocity is 0. It's a vector, 0, I guess. What's my average speed for that journey? Oh, now I do have an average speed. So to get the average speed, I need the distance traveled divided by the elapsed time. So the average speed, that's V av with no arrow over it, is, so that's the distance traveled divided by the time elapsed. And the distance traveled is, I go 300 meters one way and then 300 meters the other way. So it's 600 meters in 300 seconds, which is 2 meters per second. So my average speed for this journey is 2 meters per second. In this case, I guess I had 3 meters per second. And in this case, it was 3 meters per second west. So, first question. My average speed on my bike here was 3 meters per second. My average velocity was 3 meters per second in the west direction. And then I wound up back where I started in the third question, so that was a displacement of 0, therefore it is an average velocity of 0. And my average speed for that last journey, which was part walking and part biking, was 2 meters per second. And to get that, I had to use the distance traveled. To get the distance traveled, I had to split the journey up into segments, starting a new segment every time I changed direction. Whoa, What is the relationship between speed at a given instant and velocity at a given instant? Well, speed is a scalar quantity. It does not have a direction associated with it. Velocity is a vector quantity. It does have a direction associated with it. And the speed at a given instant is the magnitude of the velocity at that instant. So, speed, v, is the magnitude of velocity, v. Okay, so v is the magnitude of the vector v. And it's probably easier if we make it more concrete. What does calculus say about the relationship between speed and distance traveled? Oh, gee. I think that speed is the rate of change of distance traveled. Yeah, I say that speed is the rate of change of distance traveled. Speed is the rate of change of distance traveled. So, therefore, you could say that, I guess you could say the speed is the derivative of distance traveled with respect to time. I think that's a true statement. You could say that the distance traveled is the integral of the speed with respect to time. That might be a little bit scary, but we could say that. So I think calculus says those things. What does calculus say about the relationship between displacement and velocity? Does one of them equal the rate of change of the other? Well, yes, I think that velocity is the rate of change of displacement. So I would say that velocity, v, is the rate of change of displacement, delta r. So I guess that means that v is d delta r dt. But actually, the thing is, delta r is just where you are now minus where you started, and where you started is a constant. And the rate of change of a constant is 0. So it's the same thing as dr by dt. So in other words, you could say velocity is the rate of change of position. It's the same as velocity is the rate of change of displacement. Because what distinguishes displacement from position is that displacement is your position now minus your initial position. And your initial position is a constant, so the time derivative of a constant is 0. So you could say velocity is the rate of change of displacement. You could also say velocity is the rate of change of position. This is easier to write. So velocity is a vector. Velocity is the rate of change of position with respect to time. So we have here v is dr by dt. So here, velocity, v is dr by dt, which it has three components, vx, vy, vz in 3 dimensions. And so then component by component, they equal dx by dt, dy by dt, and dz by dt. Speed v is the magnitude of the velocity vector. So in 3 dimensions, this will look like, but you can cover your ears if you want to. This will look like vx squared plus vy squared plus vz squared square root of. But we're only working in 1 dimension for the first 9 chapters. So in 1 dimension, the speed v is just the absolute value of v sub x, which is the absolute value of dx by dt. At a given instant, we can talk about velocity. So if we're looking at a curve of x versus t, we can look at one particular point in that curve and say, what is the x component of velocity at that point? We can say, what is the speed at that point? Over some finite time interval, from t initial to t final. So not just at one instant, but over some time interval, we can talk about the average velocity during the time from t initial to t final. So the definition is v average is delta r. So v average, so the average velocity is the displacement, which we call delta r, divided by the time interval, t final minus t initial. We're really only interested in the x component for the moment. So the x component of average velocity, which you could say vx comma average, you could say v average comma x, is x final minus x initial divided by t final minus t initial. Okay, so we'll use this often. The average speed during some finite time interval from t initial to t final is called the distance traveled divided by the time interval. So the average speed, so v average speed, v average is the distance traveled divided by the elapsed time. So if you want the average speed, you have to work out the distance traveled. Remember, the distance traveled requires figuring out where you change direction. So the average speed is the total distance that you traveled divided by the time interval. Whereas the average velocity is the displacement vector divided by the time interval. Or the x component of the average velocity is the change in the x coordinate divided by the time interval. These are all easier by example, I think, than in generalities. When you read through chapter 2, you will find example 2.9. So I've taken that same example, but I've added some different questions to it. So we'll use the values in his table 2.1, which comes from example 2.9, and we'll answer the following three questions. So let's just consider the motion between frame 13 and frame 19. So that's just this bottom part here, 13, 14, 15, 16, 17, 18, 19. So what is his average speed over this time interval? Okay, so the average speed, so actually one thing you can notice, so it also corresponds to this little segment, and he's always walking backwards, so he does not change direction. He does change direction up here, but this is after he's already changed direction. So he's not changing direction in this interval. He's not changing direction in this interval that we are considering, so we can just take the distance between his starting point and his ending point for the distance traveled. So what is his average speed over this time interval? So we have the average speed is the distance traveled divided by the time elapsed. That's t final minus t initial. So in this case, his distance traveled is between 4.6 meters and 3.4 meters. So that is 3.4 meters minus 4.6 meters, the absolute value of that, divided by, and then this is 6 seconds minus 4 seconds. So that seems like 1.2 meters divided by 2 seconds, which is 0.6 meters per second. Okay, so it seems like his average speed is 0.6 meters per second in that time interval. What is the x component of his average velocity over that time interval? Well, I guess we can say v x average, which is the same as v average x. That is x final minus x initial divided by t final minus t initial, and which one is final is 3.4. So that is 3.4 meters minus 4.6 meters divided by 6 seconds minus 4 seconds. So that seems to be minus 0.6 meters per second. Okay, so minus 0.6 meter per second. Okay. Write the average velocity during this time interval in terms of the unit vector I hat. Oh, yuck. Okay. So we'll see unit vectors in a moment. Anyway, the unit vector I hat has a length of 1 and it points along the x-axis in a positive x-axis direction. So, and it's actually equivalent to the vector. So I hat is basically like if you wrote an ordered pair 1, 0, or if you wrote an ordered triplet 1, 0, 0. So it has a 1 in the x direction and it has nothing in the y or z directions. So the unit vector notation will be the part of this chapter you like the least, I think. So his average velocity during that time in terms of the unit vector I, so I'm going to say v average, the vector is minus 0.6 meters per second I hat. But I think you could equivalently say v average equals 0.6 meters per second backward. So if you say 0.6 meters per second is a magnitude, backward is a direction. So this is written as a vector. So if you want to avoid the I hat stuff, you can just use a word for the vector direction. So v average is 0.6 meters per second backward. Or you could say v average is minus 0.6 meters per second forward. That's the same thing. Minus 0.6 meters per second forward is the same as 0.6 meters per second backward. Okay, we have here a graph which has displacement x on the vertical axis, and it has time, t, on the horizontal axis. Time goes from 0 to 30 seconds. Displacement goes from 0 to 16 meters, although you can see the largest value that actually happens is 15 meters. So which statement best describes the motion depicted by this graph? I walk 1 meter per second forward for 10 seconds. Then I rest 10 seconds. Then I walk 1 meter per second backward for 10 seconds. Well, okay, I guess, and then other ones say I walk a half meter per second forward. So I guess they all say forward, so I have to figure out how fast am I walking forward for the first 10 seconds. How would we do that? So over the course of the first 10 seconds, it seems like I travel 10 meters of displacement. So if I have a displacement of plus 10 meters over a time interval of 10 seconds, that is an x component of velocity, or in other words, a velocity in the forward direction of 1 meter per second. So I think I do walk 1 meter per second forward in the first 10 seconds. So that seems to be true. That means I don't like this one, and I don't like this one, but this one also could be okay. So I guess we've narrowed it down to 2 possibilities now. Then I rest 10 seconds. I guess they all say that, so that doesn't give us any information to rule out an answer here. Then I walk 1 meter per second backward for 10 seconds versus then I walk a half meter per second forward for 10 seconds. Okay, so this is resting for 10 seconds. This is going forward. So what's happening here? So in this little segment, am I going forward or backward? Well, I think I'm still going forward because x is increasing as time increases. So I don't think I'm going backward. So I think that this one can be ruled out. But let's see if this rate at which I'm going forward makes sense. So it seems like I go from x equals 10 meters to x equals 15 meters in the time interval from 20 seconds to 30 seconds. So that is a displacement of plus 5 meters in a time interval of 10 seconds. So that's plus 1/2 meters per second. So I think I like that. So I think answer D looks pretty good to me. What is my average velocity during the 30-second interval shown on this graph? So the time goes from 0 to 30 seconds. Displacement goes from 0 to 16, but really 15 is the largest point in meters. So my average velocity, oh, and by the way, remember that I hat is the unit vector pointing forward along the x-axis, in other words, pointing in the direction in which x increases. Okay. So I don't really like the I hat stuff, but I'm going to use it just enough that it doesn't look too unfamiliar when you see it in the book. So V average is the displacement, which is a vector, divided by the time interval. So we also call the displacement delta R divided by TF minus TI. Okay, and what is the displacement? So, oh, by the way, that also, the displacement is, it's like R final minus R initial. Okay, T final minus T initial. So what is my displacement? My displacement is 15 meters forward. So I would say this is 15 meters forward divided by 30 seconds. So that is 0.5 meters per second forward. Forward is along the positive x-axis. So the I hat is the unit vector along the positive x-axis. So we could say we could say 0.5 meters per second I hat. That would be fine. We can do that. I don't usually like to use I hat, but there it is. So I think I like this one, plus 0.5 meters per second I hat. The I hat means in the direction of the positive x-axis, in the direction in which the x variable increases, in the forward direction. What is my instantaneous velocity, v, at time t equals 5 seconds? And then also, what is my instantaneous velocity, v, at time t equals 15 seconds? Well, v is the rate of change of position. And actually, what is the x component? So in fact, v sub x is dx by dt. So if you want to know what is my velocity in the x direction, it's just dx by dt. So at time 5 seconds and at time 15 seconds. So what is dx by dt here? It seems to be it would be that slope. And what is dx by dt here? It would be that slope. So it seems like at 15 seconds, dx by dt is 0. But what is it at 5 seconds? So I guess we can just take advantage of the fact that this is a straight line to figure out what its slope is. So it seems like it goes from 0 to 10 meters, same time as it goes from 0 to 10 seconds. So that would be 1 meter per second. So it seems like at t equals 5 seconds, the x component of velocity is plus 1.0 meter per second. So that's the only component that there is. Therefore, v is, you could say it's plus 1.0 meter per second forward, or you could say it is plus 1.0 meter per second I hat if you want to use the textbook's unit vector notation. At t equals 15 seconds, d sub x is 0 meters per second. The slope is 0. Therefore, the velocity vector is 0 meters per second. I guess you could say forward, you could say backward. It's the same for 0. So I would say that is 0 meters per second in the I hat direction. So it seems like I like answer A here. So plus 1.0 meter per second I hat, which is the same as saying forward, and 0 meter per second I hat. I hat is the same thing as saying forward. Okay. Notice that in the previous example we had to use the slope of the x versus t curve to figure out the relevant velocity component. Well, you could even say the relevant speed. So the slope of the curve of the x-coordinate versus time. Okay. Position versus time graph. The slope of the curve in the x-coordinate of position versus time. In other words, the slope of the graph of x of t versus t for an object's motion gives, is it speed? Is it acceleration? Is it average velocity? Is it not covered in today's material? Or is it the x component of the object's instantaneous velocity? The slope of the x versus t graph is the x component of the object's velocity at that instant. In other words, it is the x component of the object's instantaneous velocity. You walk 1,200 meters due east from home to a restaurant in 1,200 seconds. You stay there for 3,600 seconds, and then you walk back home, taking another 1,200 seconds. What is your average speed for the trip? Well, the average speed is the distance traveled divided by the elapsed time. And it seems like we have we have 3 segments. We walk east, and then we dwell and kind of do nothing, and then we walk west. So to get the distance traveled, we have to say how far do we go east, and then how far do we go west. Now, actually, you know that the distance that we traveled east was 1,200 meters, and then we just go back home. That's another 1,200 meters. So I guess the distance traveled was just 2,400 meters, because we walked from home to the restaurant, which was 1,200 meters, and then we walked back. So 2,400 meters was our distance traveled. And the time was, total time is 1,200 seconds plus 3,600 seconds plus 1,200 seconds. So I guess that's right. So that's 1,200 plus 3,600 plus 1,200 seconds. So you add those two and you get 6,000 seconds. So you take 24 divided by 6 is 4. So this is 0.4 meters per second was my average speed. Okay, so we had to kind of break it up into, we did a little bit in our head, but we had to break it up into segments. So there's a distance of 1,200 meters, and then there's a distance of 0, and then there's a distance of 1,200 meters. We had to add those 3 segments, and then there's the time. There's 1,200 seconds, then there's 3,600 seconds, and then there's 1,200 seconds. So then total distance upstairs, total time downstairs, 0.4 meters per second. Okay. Same scenario. What is your average velocity for the trip? Well, the average velocity is my displacement divided by the change in time. So that's just delta r divided by tf minus ti. So for example, the x component of my average velocity is just x final minus x initial divided by the change in time. And, well, I start out at home, and then at the end, I'm back at home, and meanwhile the difference was 6,000 seconds. So I guess it's 0. So I think this is 0. Maybe there's some units, meters per second. So I think in this case, because my displacement for the whole trip was 0, I ended the same place I started. So my displacement for the whole trip was 0, therefore my average velocity for the whole trip was 0. Ha! So I think I like this one. You drive an old car on a straight level highway at 20 meters per second for 20 kilometers, which is 20,000 meters, and then the car stalls. You leave the car and, continuing in the direction you were driving, you walk to a friend's house 4 kilometers, that's 4,000 meters, away, arriving 1,000 seconds after you began walking. Whoa. What is your average speed during the whole trip? Well, average speed is the distance traveled divided by the elapsed time. So what is the elapsed time? Well, I guess we don't... Gee, this is tricky, right? So what is the distance traveled? We have two segments. One is 20,000 meters. Let's say 20 kilometers. And the other one is 4 kilometers. So we know the distance traveled. What is the time? So it seems like the second segment is 1,000 seconds. How long does this first segment take? Well, I guess we have 20 meters per second. Oh, that's upside down. So you know that distance is speed times time. So the time is the distance divided by the speed, which is 20,000 meters divided by 20 meters per second, which is 1,000 seconds. So it seems like this 20 kilometers at 20 meters per second, the time that took must have been another 1,000 seconds. So this seems like 24,000 meters divided by 2,000 seconds, which is 12 meters per second. Oh, there we go. So our average speed for this trip was 12 meters per second. One thing that was tricky about this is that we were, in order to figure out the time for this first segment, we had to divide the distance by the speed. There was also some tricky stuff with meters versus kilometers. Here's a graph of position in meters versus time in seconds. So the time goes from 0 seconds to 1 second. The distance, the position goes from 0 meters to 0.35 meters. Where is the object moving forward? What does forward mean? Forward means that the x component of velocity is bigger than 0. That means dx by dt is bigger than 0. That's what forward means. Moving forward. It's moving forward, its velocity has a positive x component. Well, if we're just in one dimension, right? So moving forward along the x-axis means that the velocity in the x direction is positive. So where is that true? That's where the slope of this curve is positive. So I would say it's moving forward in that interval. Where is the object moving backward? I would say it's moving backward in this interval. So I'd say it's moving forward for t less than or equal to 0.45 seconds. It's moving backward for t, let's say, greater than 0.45 seconds. Maybe this is less than. Where does the speed equal 0? Oh, well, I guess the speed, so we know that in one dimension, the speed is just a magnitude, the absolute value of dx by dt. So that's the absolute value of the slope. So where does the slope appear to be 0? I think there's one point where the slope is 0, and that is here. So this is at t equals 0.45 seconds. Oh, where is the speed largest? Well, the speed is the magnitude of the slope. So that's not the same as where is the slope largest. It's where is the slope largest in magnitude. So the slope seems pretty big here, and it seems pretty big here. Which one is bigger in magnitude? Well, let's see if we can work that out. We want to try to figure out whether the magnitude of the slope of the x versus t curve, in other words, the magnitude of the x component of velocity, in other words, the speed. We want to figure out whether the speed is bigger over on the far left side of this graph or the far right side of this graph. Those are both places where the slope of the curve appears to be pretty large in magnitude. So which one is a larger magnitude? The one way to do it by eye is to notice that in this case, we have gone 0.05 meters in this much time. In this case, we've gone 0.05 meters the other direction in a smaller time. You see, because this time interval is smaller than this time interval. So I think, therefore, this slope is larger in magnitude. So I would say the speed is largest at t equals 1.0 second. Now, where is v sub x? That's the x component of velocity largest. Well, that's not saying where is this magnitude largest. Remember, this is dx by dt. So it's not where is the absolute value largest. This is where is dx by dt largest. So in that case, it's going to be over here at t equals 0 seconds, because this is a negative dx by dt. So a positive dx by dt is always bigger than a negative dx by dt. But, this slope is bigger in magnitude than this slope, but this slope is negative and this slope is positive. So a positive slope is bigger than a negative slope, but of course this negative slope has a bigger magnitude than this positive slope does. So I would say the speed is largest at t equals 1 second, but v sub x, the x component of the velocity, is largest at t equals 0 seconds. So the thing is, you have to consider the sign, and you have to consider whether you want the magnitude, which is for the speed, or you want the x component, which is for the x component of the velocity. Here's the same curve again. We have a different set of questions. So for this motion represented in this figure, what is the object's average velocity between t equals 0 and t equals 1 second? Well, let's just look at the x component. So vx average is x final minus x initial divided by t final minus t initial. X final is 0. X initial is 0.1 meter. And t final is 1 second. T initial is 0 seconds. So it seems like the x component of the average velocity is minus 0.1 meter per second. So therefore, v average is, well, you could say minus 0.1 meter per second I hat, or you could say 0.1 meter per second backward. What is its average speed during this same interval? Well, to get its average speed, so average speed is the distance traveled divided by the elapsed time. And the distance traveled, so you see it's going forward here, and then after that it's going backward. So we need to add those two distances. So here's one distance, and then here's the other distance. So we need to add those two distances to get the distance traveled. So we have 0.1 up to 0.3. So that's 0.2 meters going forward, and then from 0.3 down to 0. So then we have 0.3 meters backward. And then what's the time? The time is 1 second total. So that is 0.5 meters in 1 second, which is 0.5 meters per second is the average speed. So I guess this is 0.5 meters per second. Why is the average speed different from the magnitude of the average velocity? See, the magnitude of the average velocity is 0.1 meter per second, but the average speed is 0.5 meter per second. Why is that? Well, it's because it changed direction. So if it changed direction, then the average speed is different from the magnitude of the average velocity. That's just like if it changed direction, then the distance traveled is different from the magnitude of the displacement vector. So if you are accustomed to writing vectors in a plane as ordered pairs, or maybe you've used ordered triplets to write vectors in three-dimensional space, then we can say that the unit vector in the x direction, I hat, you could call it 1, 0 in the plane, or if you're in three-dimensional space, you could call it 1, 0, 0. And then we could make another unit vector j hat in the y direction, which would be 0, 1 in the plane, or it would be 0, 1, 0 in three-dimensional space. And we could make k hat, which is a unit vector in the plus z direction, which would be 0, 0, 1. And then if you had a vector, let's say x, y, z, you can write that. That's the same thing as x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. Therefore, it's the same thing as x times I hat plus y times j hat plus z times k hat. So it is often convenient to define a coordinate system where the x-axis points east, the y-axis points north, and the z-axis points up. And the origin is at some specified location. Maybe it's at the center of the ground floor of the building you're working on. Then if I'm standing 5 meters east of the origin, my position is at plus 5 meters I hat, which we could also write as plus 5 meters, 0, 0. If I'm 3 meters west of the origin, then I'm at minus 3 meters I hat, which you could write as the ordered triplet, minus 3 meters, 0, 0. Or if I'm 2 meters north of the origin, my position is plus 2 meters j hat, which is the ordered triplet 0, plus 2 meters, 0. So most students really dislike the unit vector notation from the textbook, so I try not to write it. Instead, I'll say the displacement is plus 5 meters east, or I'll use a word like east, or north, or up, or forward, or backwards, so that way I avoid writing I hat and other unit vectors. But you should know what they are because you'll see them in the book. So I hat is the unit vector that points in the direction in which x increases. That's the only unit vector you'll see for now. Once we get to chapter 10, you'll also see j hat, which is the unit vector that points in the direction in which y increases. So vectors are pretty useful. Like if you ever, like on a two-dimensional map, you have longitude is one coordinate and latitude is the other coordinate. You have geocodes, so it's like latitude, longitude. Or in a 3D CAD model, you'll have x, y, and z coordinates as you put together the vertices of every triangle or the vertices of every polygon. Again, for the first 9 chapters of the book, all of our problems will be one-dimensional. So we're only going to use the x-axis. If we have a vertical problem, we're going to call the vertical axis x. That makes the use of vectors seem a little weird at this stage because you're accustomed to vectors being like pairs or triplets of numbers, things that have more than one possible way they can go. But it is still important. If we're talking about displacement forward is different from displacement backward. Even if we can only move in the east-west axis, 5 miles east is different from 5 miles west. So it's still a vector. It still has a direction in addition to its magnitude. It's just that it's only along a single axis. So in one dimension, the position is r, which you could say is x, 0, 0. So that would be x times I hat. Then the x component of the vector v, so if we have a vector v, its x component is v sub x. And in one dimension, you would say v, I guess you could say it's like v sub x, and then there's no y component, and there's no z component, so then that's just v sub x times I hat. Since I hat it's just a thing that points in the x direction. I would say that the I hat, as far as I'm concerned, I hat is 1, 0, 0. The x component of the vector r is just x, right? Because r is a special case. It has x, y, z instead of vx, vy, vz. You don't know what letter do you associate with x, y, z. So you call it r. Okay, the position, like the radius. So in one dimension, the magnitude of the r vector is just the absolute value of x, and the magnitude of the velocity vector is just the magnitude of the x component of velocity. So I think you'll see vectors seeming more familiar when we get to jet motion in a plane in chapter 10. It's probably where you first saw vectors in secondary school, was in the context of ordered pairs in a plane. Here's just a recap of notation. Position is where is the object located in space. So it's this vector r, which has components x, y, and z, although it only has a single component x for the first 9 chapters. Displacement is where is it with respect to some earlier position. So there's delta r. It has components delta x, delta y, delta z. And I guess if you wanted to, you could call this, you say this is delta x, and that's the I hat direction. And then you have delta y, and that's the j hat direction. Then you have delta z, and that's the k hat direction. Again, I don't really like the unit vectors either. Position and displacement are both vectors. They have both a direction in space and a magnitude. Distance is a scalar. So a distance has a magnitude only, and a distance is never negative. Scalars can be negative, but distance is a positive, is a non-negative scalar. So distance has a magnitude, it doesn't have a direction, and distance is always non-negative. So we have these unit vectors. I hat is in the x direction, j hat is in the y direction, but we won't use y for the next 9 chapters. K hat is in the z direction. I don't think we'll ever use k hat in this course. So they point along the x, y, and z axes, and they have unit magnitudes. That means there's just a 1 there. Length is 1. Okay, so but these unit vectors, again, I think they'll just confuse you. So you can ignore them if you want to, I guess. So average velocity, v average, is just the displacement divided by the time interval. Okay, and in one dimension, v average, the x component, is just x final minus x initial over t final minus t initial. Instantaneous velocity is dr dt. So that would have components dx by dt, dy by dt, and dz by dt. But again, we're only working in one dimension for now. So in one dimension, v sub x is just dx by dt. Okay, so the x component of velocity is the slope of the x versus t curve. It's just the rate of change of x with respect to time. Velocity is a vector. Velocity has a direction in space. Speed is a scalar. Speed only has a magnitude. In fact, speed is the magnitude of the velocity vector. So I think for many people, the hardest part of chapter 2 will be the author's notation. You have to get used to it. It is highly self-consistent, but it takes some getting used to. Since you've made it this far in the video, here's a hint for a reading question. So what is a vector and what is a vector good for? Well, here's what a student who took the course several years ago said. They said, a vector quantity, unlike a scalar quantity, is one that not only has a magnitude but also a direction. An example of an important vector quantity is displacement. Unlike distance, displacement takes into account the direction that something has traveled. In other words, while someone might have run a 400-meter distance on a track, their displacement could be 0 since they might end up back where they started. So if you end up back where you started, your displacement is 0 even though your distance traveled might be 400 meters that you ran around the track. By the way, this is a really clear and complete answer. Clear and complete answers to reading questions always impress me and make me happy. What are 2 examples of vectors that are focal points of chapter 2? Well, I would say displacement is one, or you could say position, but position or displacement, that's one. The other one is velocity. Velocity is a key topic of chapter 2. So I would say either position and velocity or displacement and velocity. So here are a few things that I think over the years people have found confusing about chapter 2. It does take a while to get used to the vector notation. Some people really dislike it with all the subscripts. But it is extremely self-consistent. So once you learn how to read it, then other equations will just kind of make sense because they're all labeled in the same self-consistent way. So even if there are a lot of annoying subscripts and superscripts like I for initial, F for final, and then the X direction and average and so on, the same notation is used highly self-consistently throughout the book. So I think you will, even if you don't like it, you'll appreciate how self-consistently it's used. This book, by the way, is excellent on the concepts. If you learned equations in a high school physics course, but you didn't learn concepts, then you might have come away thinking that physics is boring because you're just plugging things into equations and it's meaningless. Whereas if you really learn the concepts, then the equations become not things to memorize. The equations just become the way that you take the concept and express it in the language of mathematics. So it really then becomes all about the concepts. So I really like the way this book puts the concepts first. By the way, there are lots of equations in these chapters, and it's going to take your brain some time to get used to looking at lots of equations again, especially if it's been several years since your most recent math course. So don't worry about that. It'll be true for half the class that they haven't taken a math class in a while and their math brain is taking a while to warm back up. That's perfectly normal. The unit vector stuff, again, yuck, but I wanted to talk about it enough that you see what it is, but in our own problems, we'll say things like forward or backward or east or west. We won't say I hat and J hat very often. Okay, again, the use of vectors seems a bit contrived at this stage because there's only one direction we're going. The displacement vector versus the position vector is a little bit hard to keep straight. Displacement is your position now minus your position earlier, whereas position is just your position now. The difference between average and instantaneous velocity, that's tricky. Average is during some finite interval of time, whereas instantaneous is at one instant in time. So, average is basically using some delta t, like some delta x and some delta t, whereas instantaneous, you're using calculus. You're saying dx by dt. If you have anything to add to this list that you found confusing in the chapter once you get to it, be sure to let me know in your answers to the reading questions. Okay, and then next time, we're going to move onward to acceleration. By the way, you might wonder, why are we talking about velocity now and then next time about acceleration when architectural structures generally do not move? And the answer is, we want to come away understanding very clearly, we want to have a solid understanding of forces and torque. And in order to understand force and torque, which are phenomena that cause motion or that cause things to accelerate, cause things to rotate, In order to understand force and torque, we need first to discuss motion, because force and torque are things that affect motion, so we really need to have the language for describing motion before we can then talk about, well, how do forces and torques potentially cause or change motion.